Hey there, future engineers. Welcome to The Explainer. I'm your host, Katie, and as an engineering professor, I gotta tell you, there is absolutely nothing I love more than seeing that light bulb go off, that amazing aha moment when complex mechanics finally just click. Today, we're totally mastering DEX 1084, Engineering Statics, and we're zeroing in on moments and equivalent loads. Whether you're heading into mechanical, civil, or industrial engineering, understanding exactly how forces apply to real-world structures is, well, it's absolutely critical. I mean, think about massive cranes, complex structural frames, heavy industrial machinery. It is literally these exact foundational calculations that keep those structures completely sound and fully operational. So go ahead, grab your calculators, boot up that spatial reasoning, and let's dive right in.
All right, so here is our game plan for today's study session. 1. The core theory of the moment. 2. Real-world applications. 3. Angled forces. 4. A knowledge check on equivalent loads. And finally, 5. An exam prep summary. Let's get to it.
Section 1. Core theory. The moment.
Okay, before we start crunching any numbers, I want you to really visualize what we're actually doing here. In statics, we aren't just looking at straight lines. We're looking at the 3-day turning effect of a force acting on a rigid body. Basically, it's the twist. When you apply a load off-center, things naturally want to twist. And as engineers, we need to completely control that. To quantify that twist, we use the moment, which is also sometimes called torque. M equals F times D. So the moment is the force in newtons multiplied by the perpendicular distance from the pivot in meters. Seriously, burn this into your memory. The unit is Newton meters. And remember, this is a huge trap. If the distance isn't perfectly perpendicular to the force line of action, you can't just multiply them together. You absolutely must find that perpendicular intersection.
Moving right along to Section 2, Real-World Applications. Now that we've got the theory down, let's see how this plays out in the physical world. Think about just opening a simple door. It's a perfect real-time 3D example of a lever arm in motion. Step 1. We identify the applied force. Let's say we have a 20 Newton push right on the edge of the door. Step 2. We measure the perpendicular distance to our pivot point, which is the hinge. In this case, it's 0.7 meters. Step 3. We just calculate it out. 20 newtons times 0.7 meters gives us 14 Newton meters. So that door swinging open, that is literally a 14 Newton meter turning strength in action. So what happens when you throw multiple forces at a single rigid body? Well, think about a seesaw. Child A applies 300 newtons of force at a 2-meter distance from the center. That creates a 600 Newton meter clockwise moment. Child B is a little bit heavier at 400 newtons, but sits closer to the pivot at a 1.5-meter distance. And surprisingly, 400 times 1.5 is also 600 Newton meters, just in the counterclockwise direction. Because these two forces perfectly cancel each other out to a net zero, the seesaw sits perfectly still. It's in perfect static equilibrium.
Section 3. Angled forces. Out in the real world, whether you're analyzing aerodynamic forces, adjusting a jet's wing flaps during a flight path, or calculating ground reactions guiding a heavy toboggan down a snowy hill, forces rarely line up perfectly perpendicular. We often have to deal with inclined forces. For example, say we have a 10 Newton force applied at a 0.5-meter distance, but it's coming in at a 50-degree angle. Our golden rule here? Only the perpendicular component matters. Step 1, we just modify our formula to M equals F times D times sine theta. Step 2, plug in our numbers, 10 newtons, 0.5 meters, and sine 50. Step 3, sine 50 is roughly 0.766. Step 4, multiply the whole shebang out, and we isolate the true moment, which is 3.83 Newton meters. You see, only that specific perpendicular component is what actually produces the turn.
Let's do a quick recap of these examples, but I really want you to focus your attention on that second to last row. We have a massive 98,000 Newton force. I mean, that is a gigantic industrial load. But check out the distance. It's 0. Because that line of force passes directly through the pivot point, it has absolutely 0 turning effect. 0. In civil engineering and modern industrial maintenance, intentionally directing massive loads straight through the joints is exactly how you prevent structural twisting and keep things from falling apart.
Section 4. Knowledge check. Equivalent loads.
All right, folks, it's time to test those cognitive skills. I highly encourage you to actively pause the explainer right now, grab some scratch paper, and try this yourself. Ready? Challenge 1. A 100 Newton vertical force is applied right at the very end of a lever attached to a shaft. The question asks us to determine the moment of O. Go ahead and pause. Think about it for a second. Okay, did you spot it? What crucial piece of information is actually missing to solve this? That's right, the perpendicular distance from O to the end of the lever. To find the answer, your equation simply needs to be m equals 100 times that missing length d.
Okay, let's step it up to a true exam level question. We've got 3 different loading systems, A, B, and C. The question is, which ones are statically equivalent? Your strategy here has to be evaluating the resultant force, R, and the resultant moment, MA, about point A for every single one of these systems. Take a close look at the parameters. Pause the explainer again, run your equilibrium equations in 2D space, and see which systems actually match up.
And we're back. Did you run the numbers? How did you do? The answer is systems A and C are statically equivalent. Massive congratulations if you nailed that one. Grasping equivalent loads is a really huge milestone in your statics journey. So let's actually break down exactly why A and C match. Let's look at the solution strategy for system A. Step 1. We have an applied leftward force of 44.5 newtons, which means our resultant force vector R is negative 44.5 on the x-axis and 0 on the y-axis. Easy enough. Step 2. The moment at point A. We start with 108.5 newton-meter clockwise moment, so that's negative 108.5. Now we add the moment from our horizontal force, a 1.829 meter force arm multiplied by 44.5 newtons. Step 3. Let's calculate. Negative 108.5 plus 81.4 gives us a resultant moment at A of negative 27.1 newton meters. If you go ahead and run system C through the same process, you're going to find it yields these exact same resultant values. Pretty cool, right?
Section 5, Exam Prep Summary. Wow, we have covered some truly fantastic ground today, from analyzing the force of just pushing a door to evaluating complex 3D statically equivalent systems. Let's go ahead and lock in this ultimate cheat sheet for your final exams. First, remember that the moment always equals force times the strictly perpendicular distance. Second, if your force vector passes straight through the pivot point, your moment is a big old 0. Third, for angled forces, you gotta break out your trigonometry because only the perpendicular components count. And finally, always track your spin. Clockwise and counterclockwise directions will completely dictate your positive and negative signs. Master these core concepts, and I promise you, analyzing simple trusses, frames, and composite bodies is going to become second nature. You are now officially equipped to handle 2D and 3D rigid body equilibrium. So I'll leave you with this thought. The next time you look at a towering skyscraper or an intricate, heavy-duty machine in a factory, ask yourself, with these core statics principles mastered, how will you apply statically equivalent loads to design the complex 3D structures of tomorrow? Keep calculating, stay curious, and I will see you in the next explainer.